Hey everybody, today we're going to take our first look at amplifiers. I'm Michel Maharbiz.
And I'm Vivek Subramanian. Let's get started. So the first thing to do when we're talking about amplifiers is to start defining the various inputs and outputs to an amplifier. What I've shown on the top of the screen is a standard schematic representation of an amplifier. In a standard schematic, we represent an amplifier as a triangle. And you'll notice that this triangle has multiple pins, multiple terminals going into or out of it. Specifically, you'll notice there's an input labeled V in, that would be the input voltage. There's an output labeled V out, that's the output voltage. Now, of course, you know that voltages in general have to be referenced relative to something else. And in particular, it is common to reference the input and output relative to a common reference terminal, which we've called ground. An amplifier may have a ground reference, therefore, as a result. Now, in the last section where we talked about a bipolar amplifier, you saw that it's necessary to have a power supply in addition to having the input and output. And the power supply is used to deliver the necessary power to achieve the amplification from the input to the output. In a standard amplifier, we will typically have two power supply nodes labeled VPOS for a positive voltage, and in this case we've labeled minus absolute V neg to represent that there's a negative voltage as well. So what you notice, Michel, is we have a VPOS, we have a minus V neg, and we have a ground. Any idea why we have a VPOS and a V neg?
Well, so the ground is just, I guess, what you said. It really gives us the reference for V in and V out since voltages are differential. So my guess is that the positive and negative supply terminals are giving us the limits that the output can achieve. So if, let's say, I put plus 5 at V pos and minus 5 at V neg, the amplifier would really only be able to produce voltages between minus 5 and plus 5.
That's right. If you remember in the previous example, I had put constraints on you when we were looking at that bipolar amplifier. I had put constraints on how high or how low the voltage could go, and they were related to the power supply. So that's exactly right. We have the reason we put a positive and a negative supply is so that the input and output can swing above and below ground.
And these are called the rails. So usually the plus and minus rails are V pos and minus V.
That's right. Now within the amplifier, it's got circuitry inside. Within this triangle, we're essentially representing a complex circuit, and that circuit may contain resistors, capacitors, transistors, and in some cases, particularly in some high-frequency amplifiers, we'll see things like inductors and transformers as well.
Yeah, in fact, when we do real op-amps in the next slide deck, we're going to actually show you a really brief look at the transistors inside a 741 amplifier, just to give you a taste of it.
And the 741 is a particular type of amplifier that we're going to look at. But one of the beauties of the way we do things, and we've been using this throughout this course, is we get to abstract things. We're not going to worry about the internal circuitry here, but we're going to find some characteristics to represent it by exploiting linearization and then use those in our analysis.
So these amplifiers come in a variety of packages, and I'm just going to go through this very quickly just to give you a flavor for what they might look like in real life. The most common and one of the older integrated circuit packages is called a dual inline package. And this is sometimes what people see like when they're in high school and they're building simple circuits, and they'll call these chips and so on. And basically it's a plastic package, usually sometimes ceramic, that has these metal pins coming off of it. They're also called package leads. You see these, and they're conductors. And inside, somewhere inside the center of this, is placed the actual silicon integrated circuit that has all of the components that are going to form your amplifier. And then little wires run from each of the tiny little metal contact pads that form the inputs and outputs of the integrated circuit. Little tiny wires, somewhere between 50 microns and maybe 125 microns in diameter, are run from there to each of these independent leads that you see here. And then the thing is sealed, it's packaged up. And then when you use it, you'll push it into a printed circuit board, which will have holes that are metal plated, and you use solder to short, to basically short or electrically connect each of these pins to the printed circuit board and off to the wires and other components you might have on the printed circuit board.
So, Michel, you mentioned those wires on the inside. Those wires are made of gold, typically. Small amounts of gold, obviously. It's not a huge amount of gold. You know why we use gold?
That's a good question. I guess my guess would be that, first off, gold is a pretty reasonable conductor, and it's a noble metal, so it probably doesn't oxidize and sort of age over time.
That's true. And also, it turns out it's relatively easy to draw gold out into thin wires because it's pretty malleable.
Oh, that's true. That's true. So there are other types of packages, and we're not going to go into them in great detail here, but for example, this type of package you can see has the same little leads, but they're much smaller and they flatten out near the bottom. And so these types of packages are actually placed on the flat surface of the printed circuit board. There aren't holes that the pins go through. And then there's solder or solder paste is used to bond up all these little leads. And you can see the density of lead is very, very high. This is an Atmel chip which will have hundreds of different inputs and outputs and power rails and so on that have to be connected to it. And then there's another class, for example, as an example, called the ball grid array, which has on the underside has these tiny little metallic regions, which are also solder paste or solder bonded onto the top flat surface of a printed circuit board. And there's a lot of these. There's lots of families and variants of these various packages depending on the need. And you can imagine as the years have rolled on and the density and the complexity of these integrated circuits has gone up, new families with very high density connections have emerged.
By now, in this series of lectures that we've provided for you, you've had a chance to look at some integrated circuits, you've seen some resistors and things like that. I'd encourage you to consider, if you have an old computer, an old cell phone, open it up and take a look and see if you can recognize some of the parts on the inside, just as a quick practical exercise.
Yeah, it's a lot of fun. Do your own teardown. You can also find lots of nice teardowns for consumer products online by just Google searching for teardown and whatever it is your product you're interested in doing. So amplifiers also have some odd packages, right, Vivek?
Yeah, that's right. In particular, amplifiers are used in a range of applications that may place constraints on the package. For example, many amplifiers are used in high-power applications. For example, your audio amplifier might be a high-power application. Now, when used in a high-power application, the amplifier internals generate a lot of heat. So we need to find a way to dissipate the heat such that it doesn't cause the amplifier to overheat and burn up. And that's commonly achieved using a heat sink. And so if you were to open up a power amplifier or the inside of a computer, you'll find lots of these heat sinks. And heat sinks are basically these large metallic fin type structures that provide a large surface area from which heat can escape to the environment.
Makes sense. There's also a bunch of coaxes there. Is that right?
That's right. These are coaxial inputs. And coaxial inputs are the types of inputs that you often see on the back of a television to which you would connect your cable from your cable, for example. And that consists of a signal line surrounded by a grounded sheath wire. And the point of that is it protects the signal line from external noise. And in many high-end amplifiers, particularly amplifiers running at high frequency, you will see coaxial cables used as the input. So these are examples of amplifiers with coaxial inputs, and the one on the left happens to have a heat sink as well.
One of many neat ways to see something like this in the context of amplifiers is to go down to your sort of local high-end audiophile store, and try out Audition, it's so to speak, a variety of different amplifiers, and you'll see that they have these giant heat sinks and many of these features we've talked about. So let's take a look at how we would define the equivalent circuits that are inside a real amplifier. And we're going to pick a voltage amplifier. It's important to point out, as we will get to later, that we can look at current amplifiers as well, or voltage to current amplifiers, or current to voltage amplifiers. We're going to pick a voltage amplifier and hit all of the main points of this. So, okay, so we've got our amplifier here. It's drawn as a triangle. And notice that we haven't drawn the ground or rails connected to this amplifier, which is pretty common in normal circuits to leave those out, even though it's assumed they're there. We just have the input and the output. So we've got our input connected to some source. This source might have a source resistance. We've sort of left it out for simplicity, but you might have a source resistance here connected to the source. So this is the input, and again, it's an equivalent circuit for whatever might be on the left. And there's an equivalent circuit for whatever might be on the right, which is modeled as a load resistor. Okay? Now, once we put this together, there's a few imperfections that we can immediately, almost using common sense, realize are probably present in a real amplifier. Okay? So first of all, there probably is going to be a current flowing in through the input node down whatever branch connects the input node to the internals of the amplifier. Okay? And there's probably some current that's going to flow down that branch. We're going to get into the equivalent circuit in a moment. But if there is a current flowing down that branch, you immediately know that this amplifier is going to have a finite power gain. So I wanted to say that again and then give you 2 seconds to think about why that might be. It's a good exercise. Why might it be that if I have a finite input current, in other words, this current is not zero, connected to whatever is inside the amplifier, the ratio of output power, in other words, the power through the load, and input power won't be infinite. There's a finite power gain. What do you think, Vivek?
Well, we can work through this in a fairly simplistic way because you've given me the parameters I need. You've told me that there's an input current, IN, and there's an input voltage, VN. That being the case, I would know that the power being consumed at the input is just VN times IN, all else being equal. And at the output, you've told me that the output voltage is V out, and I'm driving a load resistor RL. So the output power here would then be V out squared divided by RL, based on the physics we learned earlier. So that means I have a finite input power, I have a finite output power, and therefore I have a finite and knowable power gain.
Right. It's a finite ratio. If IN was 0, then you would have some number divided by 0, you get infinite power gain. Okay, now the other point about this input current is that it leads to a loading effect. And we're going to discuss that in great detail. Vivek's about to go into that in some detail. But as a preview, you can imagine that if there's any source resistance associated with this source here, if there was a little resistor R sub S, that IN times R sub S would constitute a little voltage drop, such that Vin, the voltage at this input, would not be Vs, right? It's going to be Vs minus the voltage drop across the source resistor. And so that's called a loading effect. Essentially, the moment that any current is flowing through there for any realistic input source, which will be pretty much anything, your Vin, the voltage that's presented to the amplifier for it to amplify, is not going to be exactly what is coming out of the source. Okay? The output voltage of the amplifier will likewise vary, loaded by the load resistor. Okay? So it's the same idea. If I have a load resistor here, whatever the amplifier is trying to do is going to be affected by this load resistor in terms of the current moving through there. So one way to think about this is that let's say I want to have the amplifier produce 5 volts at the output. It just happens to be what we want the amplifier to amplify the input into the output. We want 5 volts out here. Well, depending on RL, right, the current required to maintain 5 volts across this RL will determine the current, right? And so for different values of RL, I'm going to get higher or lower currents. And there may be a load for which the current is so high that this amplifier just can't supply the current required to multiply times RL to get the V out that we want. We'll come back to this in a minute. But basically, these amplifiers, a real amplifier, can only faithfully amplify for a range of output resistances or load resistances. It can't really drive anything it wants. Okay? And then very lastly, very quickly, we already sort of told you the output voltage is limited in range. It can't exceed the rail. So if I put 5 volts positive and minus 5 volts on the negative rail, those are the 2 rails, I can't generate a V out of 100 volts. No matter what I'm doing in terms of the input, it's just this amplifier cannot definitionally produce an output that's that high. Okay?
All right. So at this point, we're now ready to start looking at the internals of this amplifier, and specifically how we would represent these effects, namely the loading on the input, how the output is affected, and so on. All the analysis we're going to do now, we're going to work under the assumption that we don't have a limit on the rail. So we're not in the rail limited regime. Okay? So first, let's talk about the input resistance. And the input resistance, we model it in the same way we've been modeling resistances before. We will say we'll look into the input, we'll apply some sort of test source to the input, for example a V in, and we'll measure the current going through that, I in. We can then represent that input resistance by a resistor R in. So if we were looking at what we were to draw inside that triangle, on the input side we would likely just put this,
I see,
an R in value. Okay, so that's the first part. Now let's start looking at the consequences of this resistor. Let's say we are now driving this amplifier with a real voltage source. So a real voltage source we represent as Vs with a series resistor Rs. Okay, so we've got this real voltage source there. Well, you will recognize right away What is this, Michelle?
That's a voltage divider.
Exactly. This is a voltage divider. That means the Vin that we get is not actually the same as Vs. In fact, Vin becomes Rin divided by Rin plus Rs times Vs. In other words, the voltage that the amplifier effectively sees at its input is less than the voltage we thought we were applying.
So this is what we were discussing in terms of loading. So this is the input resistance of the amplifier is sort of loading whatever's driving it. And it matters. It actually matters deeply what the input resistance of the amplifier is.
That's right, because this loading effect is pulling a current through Rs and Rin, and that loading effect means there's a voltage drop across Rs, which is buried in this equation.
Make sense?
Okay, so then we get to the question of what was, in an ideal world, what do we want to do with Rin? What do you think, Michelle?
Well, let's see. I really want Vn to be as close to identically equal to Vs as possible, right? Because whatever voltage I'm trying to amplify, I want it to be in Vn. I want it to be equivalent to Vn, so it gets amplified. So for that to happen in my voltage divider, I guess Rin would have to be really, really big compared to Rs, because then if I look at my fraction, I get a big number divided by that big number plus something small, which is just goes to 1 as Rin goes to infinity, and so Vn equals Vs.
Right. So our goal is generally to make Rin be as large as possible.
Right.
And in fact, in an ideal world, we should tend towards infinity, but really in practice what we're saying is we want Rin to be much, much larger than Rs.
And these numbers in real amplifiers are pretty humongous, right, Vivek?
That's right. It turns out this is not really a big limitation in modern amplifiers. Modern amplifiers, Rin can approach a teraohm.
Wow.
So it can be really large.
That's amazing.
Okay, so we've now talked about Rin. Michelle, maybe you want to start talking about the output side.
Let's talk about the output side. So since the output voltage varies depending on the load connected at the output, essentially what that tells you is that the output terminal must itself have some equivalent resistance. In other words, if I'm looking in at the Vout terminal of the op amp with respect to ground, I'm looking in to the left, it's as though, like in the previous slide decks, we gave you methods for taking some complex circuit, looking into the terminals and asking what the equivalent resistance would be, right? This is the same idea. And to find this resistance, we'll use the same techniques we discussed before. For example, we can measure the open circuit voltage at Vout when no load is connected to it, and divide that by the short circuit current if I short the output to ground. Right? If I do both of those things, I can get a measure of Rout. Or I can connect a source, either voltage or current, and monitor the opposite. So if I connect a voltage source to the output, I could look and solve for the output current or vice versa.
So these are the techniques we covered when we talked about equivalence.
That's right. That's exactly right. So what basically this boils down to, though, is that there is an output, effectively an output resistor right inside the op amp at the output terminal. Now, of course, there's an internal voltage source that we're going to talk about on the next slide, which is what really does the amplification. But for now, just assume there's a voltage source here, and the key is, again, this loading. It's the same thing as happened to the input. When I connect a load to the output of the amplifier, the actual output voltage that I see across this load, in other words, whatever circuit is connected to the output of the amplifier and looking for that input, is going to see VL, right? And that is going to be different from the internal voltage that the amplifier is producing as part of its amplification. So if the amplifier is, say, producing 5 volts at the output, or trying to, what the load is actually going to see is voltage division, right? And so again, you see the same concept Vivek was fleshing out before, but in the context of the output versus the internal output resistance of the amplifier versus the load resistance. And you can see the same thing. The internal source voltage is divided by RL, divided by RL plus RL to VVL. So to push the ball back to your side, so what do we want our output resistance to be for a good amplifier?
Well, our goal here is going to be to make VL get as close to VTH as possible. In other words, we want the output voltage to be as close to what the amplifier is attempting to generate internally.
Right.
And for that to be the case, based on this voltage division formula, I would want R out to be as small as I possibly could.
That's right. It's like saying that we want the output, the inside at the output side of the amplifier to look as much like an ideal voltage source as possible.
That's right. Now, it's worth pointing out that this is a limiting factor in many modern amplifiers. The output resistance is not 0.
Right, sure. It's some reasonable number probably, yeah.
That's right. Okay, so we can put these together now, and then we can have an equivalent circuit. And the equivalent circuit has all the parts we talked about before. So let's take them one by one. We have the internal input resistance, Rin. We already talked about that. We have the output resistance, Rout. And we have this other element, which now let's talk about specifically this element, which is a gain element. And this gain element represents the gain of the amplifier. And specifically in this case, we've defined a voltage amplifier. So we use the term A sub V, and the V indicates voltage amplification. So it is a voltage-dependent voltage source. The output voltage depends on the voltage across this resistor.
I see. So when I connect something on the left side, it's going to produce, by voltage division, some V sub X in the internals of the amplifier. That will get multiplied by some value that's a property of the amplifier, some A, and then that'll be sort of sent out or through the voltage division at the output.
That's right.
Okay.
All right. So let's try to work through a real example. Michelle, maybe you can walk us through one?
Sure. So let's say we want to amplify a very weak signal. So essentially it's going to look like a very small voltage source, maybe a millivolt in max value. And let's say that it originates from a sensor. In other words, a sensor that's producing this little voltage that's changing over time. Maybe it's an electrocardiogram sensor electrode, which is telling you something about your heart. And not only is that source voltage very low, but it's got a very big source resistance. And so what that tells you is that it can't push a lot of current, right? It's a very big RS at its equivalent circuit, all right? And what we want to do is we want to take this voltage that's varying over time and digitize it, right? Because we're in maybe a hospital or something, and we want to use an analog to digital converter to record that.
So, Michelle, that value of 1 megaohm, is that a representative value that we might see in a real sensor?
Oh, absolutely. I mean, high source resistances are common in many, many sensors. And again, it's because many sensors are small. They can't push a lot of current. Often the phenomenon associated with the changes you're looking for maybe give you a certain amount of voltage, but just really can't push a lot of electrons.
I see. So it is just a very low power.
Yeah, very often that's the case, yeah. Not always, but certainly that's the case for many sensors. So anyway, so what we want to do is we want to go from this sensor to something that is recording that voltage and then doing something with it. For example, it's taking the analog voltage and digitally encoding it and storing it somewhere. Okay, now the key though is I'm going to go and look for an analog digital converter from some box somewhere, and I find that that analog digital converter would really like to see voltages that are a bit higher than what this sensor can provide. Okay? And maybe, it's not specified here, but maybe the analog digital converter also needs a bit more current. It just can't deal with a source resistance that's high. That could also be the case. And so what I'm going to do is I'm going to pick an amplifier, and I'm going to put an amplifier between the sensor and the analog to digital converter, so that essentially your sensor is on the left side here, and your analog to digital converter is on the right side.
Okay, so if I understand this correctly, what you're saying is on the left-hand side, we're going to have that sensor, which is going to be this ECG device, and then we're going to drive that into this 1 kilo ohm resistor on the input, and then on the right-hand side, we're going to take the output of the amplifier and use it to drive the ADC.
That's exactly right.
And the goal then is to take that 1 millivolt input and hopefully boost it up to the 1 volt range that we need for the ADC.
Exactly. So now let's see how good a job I'm going to do about this. So what I'm going to do is I'm going to go and get an op amp and pick some values of that amplifier, and see how well that amplifier that I'm going to pick will do the job we want. So here's what we're going to do with that. I'm going to walk you through the component values and the gain that I chose. And intuitively, even before working out the math in the next slide, tell me whether you think I'm doing a good job or not. So
I'm betting you're doing a lousy job, Michelle.
Okay, your intuition is dead on. Okay, so let's see. I'm going to naively want, first of all, I'm going to pick an amplifier that has an internal voltage gain of 20 decibels, 20 dB. Now, some of you out there might say, wait a minute, we've never seen dB. Why are these guys introducing this? But here's a good point to introduce what a decibel is. We're going to cover this in a lot more detail later on in the course, so you're probably bored to death of it. But for the moment, a decibel is really just 20 times the log 10, not natural log, of the ratio between the output and the input voltage, defined however we want V out and V in to be. So for example, let me give you an example. If I'm dealing with the gain of an amplifier, what I'm saying is that this source here produces a voltage at the node right before the 1 kilo ohm resistor that is A times this input voltage, Vx. So the ratio of the output to the input is this value, capital A. So for example, I might say A sub V is 10. Right? This output voltage is going to be, the source voltage is going to be 10 times Vx. So if my value is 10, if my A is 10, what is it in decibels?
Well, let's see. If we take V out over Vn, so you're saying V out over Vn is 10, log 10 of 10 is 1, so that means it's 20 dB, which is why you're specifying this amplifier has a gain of 20 dB.
Right. So I picked an amplifier that has an internal voltage to voltage gain of 10.
And the reason we use dB is because it's convenient for describing, because it's a logarithmic scale, we can cover a broad range of amplification values. You will find in product literature that gains are often quoted in dB, which is why we're using it here, just so that you get some introduction to it.
Yeah, exactly, familiar. And this is a dV for voltage ratios. We'll talk to you about the differences when you're dealing with power and such, so we'll get to that. But for the moment, good enough. And then I'm going to say, I want my amplifier to have an input resistance of 1 kilo ohm and the output resistance of 1 kilo ohm. So how does that sound to you?
That sounds like you're not following your own guidance. You told me earlier that we want a really high input impedance and a really low output impedance. Well, you've picked values of R in and R out that are the same, and worse still, R in seems to be pretty low compared to the sensor resistance.
That's right. This is going to be a horrible example, everybody. The idea is to show you how the sort of non-idealities of these amplifiers, these resistances, really matter when designing amplifier circuits. All right, so let's go through the math, Rebecca.
Okay, let's go ahead and work through the math. What I've done is I've gone ahead and set up the circuits that represent this system. In other words, I have the sensor here, which has its voltage source and its high resistance of 1 mega ohm. I've connected that to the input resistance, which is 1 kilo ohm. I've then got the output side of my amplifier, so it has a gain of 20 dB and a 1 kilo ohm output resistance. And I'm driving my load, which is the analog to digital converter, which we've just told you has a 1 kilo ohm resistance. All right, so let's go ahead and work through this. And I'm going to work through this in sections. I'll first start with the input section, and the reason I'm doing this in sections is I'm going to show you the effects of all the loading. And I'm going to establish for you that the gain of the amplifier that we effectively get is not going to be the 10 that we thought we had with a 20 dB internal gain.
You're predicting that this thing is not really going to amplify by 10.
I'm predicting it because I know you. So I'm going to show how bad your design was. All right, so let's start. On the input side, you'll recognize this is a voltage divider. And it's being a voltage divider, we can say that the effective voltage Vx that we see across the input resistor R in is just going to be R in divided by R in plus Rs. And we'll calculate those values in a minute, and we multiply it by Vs. So we've got the value of Vx.
So it's just a voltage divider.
It's a voltage divider. We've dealt with the left-hand side. Let's do the same on the right-hand side. On the right-hand side, again, we have a voltage divider. This time, the voltage that's fed to it is AV times Vx. So what we're going to have is RL divided by R out plus RL times AV Vx.
Wait, so let me guess. So what you're saying is to figure out the output voltage out on the load resistor from the very, very input Vs, since you already solved for Vx on the left side in that fraction, you're going to essentially plug that into the expression on the right side and kind of work out the whole thing.
That's right, but let's now introduce a term which I'll call the effective gain of the system.
Okay.
And the effective gain of the system, which I will call A sub F, is the gain that the actual system delivers us in its actual implementation with a real load and a real source. And so we'll say that is VL, the voltage across the load resistor, divided by Vs, the voltage provided at the input.
Okay, that sounds reasonable.
If we define it as such, by plugging this Vx equation into this VL equation, we can then calculate VL over Vs and get the effective gain. And that, you can see very obviously, is the specified gain of the system reduced by the loading at the input and reduced by the loading at the output.
Oh, so you've got your AV, the 10 or the 20 dB.
Right.
But it's getting smaller because there's a fraction on the left, which is the loading, the amount that Vx was reduced by, and then the fraction on the right is the amount that the sort of real true output VL was recited. That's pretty cool. Okay, so what do the numbers work out?
Well, let's see. Given the choices you made with respect to input and output resistance.
What are you trying to say? Oh, well, that's horrible.
Yep. So here's the actual gain, effective gain that we see. Because of this huge source resistance relative to the input resistances, and we see that there's a massive reduction in gain, and instead of getting a gain of 10, which is what you thought you were starting with, you get an actual effective gain of 0.005.
My, I failed my midterm. But let's try to deconstruct it. So just maybe to beat the horse dead a little bit, but on the left side, the Rn divider, really what killed us is that we had a 1 mega ohm resistor and a 1 kilo ohm resistor. So most of the voltage Vx, most of the voltage Vs isn't dropped across Vx, it's dropped across the 1 mega ohm resistor.
Exactly. The problem you had was you had a very high impedance source driving a relatively low input resistance amplifier. We also had a factor of 2 hit on the output, but the big hit was definitely on the input side.
I got it.
And you see, the result is you ended up with a gain of less than 1. In other words, you didn't get real amplification. This is the opposite of what you wanted.
A good side thing for you to do right now is to pause and substitute in say an input resistance for the amplifier of maybe a giga ohm instead of a kilo ohm, and an output resistance of 1 ohm instead of 1 kilo ohm, and look at the vast difference you're going to get.
That's right. And we'll give you a second, but when you do the math, you're going to find you get a really high gain now, much closer to the 10 that we thought we had.
Perfect.
Okay. So now, Michel, given that we've talked about this idea of these amplifiers, maybe you can walk through the idea of putting amplifiers together.
Yeah, so cascading amplifiers is very common, and it follows the same rules that were applied in the example before, except what happens is, when I cascade these amplifiers, the input resistance of this amplifier will form will become the load, the RL, for the output of this amplifier, and so on. So it's the same exact math we did, except you have 2 stages. Now, if they were ideal, it would be very easy to calculate the gain from the input to the output. You would just multiply all of the individual gains. But what happens when you, as you can, I'm sure, expect already, if you've been following what we've been saying, when you cascade real amplifiers, all of the input and output impedances do these voltage divisions, and you're going to get a lower gain if the output impedance of this is not low compared to the output impedance, the input impedance of this amplifier, and for example, the output impedance of this is not low compared to the load, and so on for the input of this amplifier. There's really not much more to it than that, but you can't simply take these things and multiply their gains unless, like I said, these voltage dividers are minimized by taking proper account of loading. Fair enough?
Makes sense to me.
Okay, how about dynamic range?
Okay. So this is the last topic to talk about. Everything we focused on so far, this idea of gain, input resistance, output resistance, assumes we are operating in a region where we are not limited by the power supply rails. Now, we told you earlier that your circuits are typically limited in terms of what outputs they can produce by the power supply rails. So what we show here is a plot of the output voltage as a function of the input voltage, and what you find is that you're never able to produce an output voltage that's greater than Vout max or less than Vout min. And these would typically be limited to the rails. So this might be your positive supply rail limit, and this might be a negative supply rail limit. Now this has interesting consequences. It means that there's only a range of inputs over which the amplifier behaves as this nice linear amplifier that we thought that it did. The slope, by the way, of this line in this region represents the gain.
That must be the gain. Yeah, that's what I was going to say. Okay.
So you see, therefore, that we've now, therefore, established a boundary space in terms of the output and, therefore, in terms of the input, and we define that as the dynamic range.
Hey, so that must have been what we were talking about earlier about linearization. So we're treating this amplifier as a linear circuit according to the circuits we just did a slide ago, but that's only true in a certain region, right? Obviously, beyond V and max and below V and min, it doesn't really work. It's not really a linear device.
That's right.
Okay.
That's right. So all those nice current voltage-dependent voltage sources and resistors that we use, those only work to model this as an equivalent circuit in here.
Makes sense. Okay.
Not at the edges.
Okay, fair enough.
So maybe you can look at some consequences of this, and perhaps you can walk through an example.
Okay, so let's talk about two concepts called clipping and distortion. And I'll introduce clipping, which is a pretty straightforward idea, and then Vivek, I think, will do a nice job of rounding this off by discussing how it relates to distortion. So let's think of maybe an audio signal. It's a voltage signal coming into your amplifier, and let's let's pretend it's sinusoidal with time. Okay. Now, clipping is something that happens when the input exceeds the linear region of the output. And at that point, you'll see, since the output can't track, it can't produce the amplified signal as we want it to, you're going to see that something funny happens to the output in those regions.
So if I understand correctly, what you're going to do is you're going to show me a time plot, essentially, of an input and an output as a function of time?
Yeah, let's do that.
Okay.
So let's start with a little piece of it. So we're watching at a time. You can see that these curves will become sinusoidal as we go on in the example. But you can see that there's an input. It's this cyan blue color, and then there's the output is this sort of magenta. And the input is coming in, and the output is tracking it. So far, so good, right? I haven't set the scales, so it could be that the output is actually in magnitude larger than the input or not. It doesn't really matter. But the point is that the output is tracking the input nicely. Fair enough?
Makes sense.
Okay, but look what happens here. Now, the input got too high. It kept increasing, and it reached a peak. But somewhere here, where you see the output flattens out, the amplifier just couldn't keep amplifying. We exceeded maybe the rails or something close to the rails. And so maybe we were putting in a volt, and our gain was 5. So we were getting 5 volts at the output here. And that maybe right at that point, we were getting 5 volts. And our rails were actually plus 5 volts and minus 5 volts. So if I went past that, we would have gotten a value higher than 5 at the output. It just can't follow. And so it flattens out. That's called clipping. And in a sinusoidal signal, of course, this repeats. A sinusoidal signal, it just sits there and oscillates in a nice regular fashion. And so what would happen is your output would actually the sinusoid would be clipped both at the top and at the bottom in every peak, every maximum, every minimum. And remember, let's take a typical sinusoidal audio signal. Maybe some high-pitched noise would be what, maybe like 8 kilohertz or something.
That's right.
And so 8 kilohertz, that's 8,000 times a second that these little things are distorted. So you might intuitively think this is probably not going to sound like a nice 8 kilohertz tone at the output, right? So I think that's a good intro. So how does this relate to distortion?
Okay, well, you've actually sort of set this up for me very nicely.
Well, thank you, Vivek.
When we think about audio, the fundamental construct we use to build audio signals is, of course, sinusoids.
Right.
A single sinusoid you hear as a monotone, as a single frequency. When you clip it, you know from your past experience, perhaps looking at Fourier transforms, etc., you've learned that this signal is clearly not a sinusoid, but in fact you can build it as a construct of multiple different sinusoids.
I see. So just to be succinct, so even if you don't know this at home, any repeating or regular waveform with time can be represented as a sum of many different sinusoids.
That's right.
So if it's a pure sinusoid like the input, that's obviously
That's
just
one.
a sinusoid. But this thing in the bottom that's more complicated, it is regular, however, it repeats. So we can have some sum of sinusoids, who knows how many, to get a good representation, but that's what you're saying. Okay,
Right.
so far so good.
Now, here's the key point. To create that sum of sinusoids, they now cover multiple different frequencies. Because, for example, at this, wherever you have these sharp edges, they will indicate that you'll have some very high frequency components built into it.
So what happens, you're saying, is that where I was hearing a nice, pure, beautiful 8 kilohertz tone, my speakers, after I ran it through my amplifier and then ran that through some speakers, it sounds like a repeating pattern, but with some distortion, with some weirdness to it.
Right. What you might hear is 8 kilohertz and 8.3 and 9 and 11 and 15 and who knows.
Okay.
Because it's whatever sum you need to create this shape.
Right.
And the ear will perceive that as distortion because it's non-harmonious. Now, you would say that's a bad thing. The example we've used where the amplifier produces it, that's an example where your amplifier is clipping, and so when you turn your amplifier to really high volumes, it sounds terrible. But on the other hand, we can also use this in creative ways. For example, guitar effects pedals. Distortion and overdrive pedals that guitarists would use actually intentionally use clipping to create the distorted sound that we use, for example, in rock or hard rock guitars.
So my guess is that different pedals color the sound, so to speak, different ways, which means that maybe they distort it in different ways, and so that's what makes it kind of interesting to get into making those things.
That's right, and in fact, perhaps later in this series, if we have time, we can actually walk through some real pedal circuits and see what they do to the waveforms.
Yeah, that would be awesome. Okay.
Okay, so that's it for now. We'll see you next time.
All right, see you, everybody.
Bye.